Greetings and welcome. In this session, we will study about the complete multi-stage compression system of the multi-pressure refrigeration system. Now here in this system, what will be exactly? So in a multi-pressure system, there are three types that we have seen in a introduction part. That is, first, these are the methods of the multi-pressure system, and especially we have seen for the two-stage compression. So first one was what? Flash gas removal method. Second was intercooling, and third is a complete multi-stage. Now this third method is a combination of first two. So here flash gas removal, that concept will be coming into picture, and secondly will be intercooling. So left side, if you see pH diagram of the system and also construction diagram of the system, then left side of the construction diagram, if you see here, left side of the construction diagram, this will be similar to flash gas removal method. If you see here condenser line, that condenser line is given to the flash tank through the expansion valve. From the flash chamber, here liquid line is taken out and then it is given to the evaporator through the expansion valve. So this same concept or same type of schematic, part of schematic, you will find in the diagram, schematic diagram of flash removal method. And if you take right hand side of the intercooling method, that is the second method, you will find the similarity. Here you can see this is a compressor 1 output that is given to the flash tank for intercooling purpose, and from the flash tank here this is a taken out and then it is given to the compressor 2. From the compressor, this is a vapor line given to the condenser. So this right side part, if you see, this will be exactly same of second method, that is a intercooling method. So that is why we call this system as what? Combination of flash gas removal and intercooling method, and that is the name is what? Complete multi-stage compression system. Now here, as we are using here this system up to two compressors, so this system becomes two-stage compression system, two-stage complete compression system. Now here we can see the remaining part, that is what? Through the compressor 1, that is a mass flow rate which is flowing, that will be what? M1 dot. Through the compressor 2, mass flow rate which is passing, that is M2 dot. So in this case, mass flow rates are in a lower envelope, means low pressure compressor envelope. Mass flow rate which is getting circulated, that will be what? M1 dot. And mass flow rate of the refrigerant which is circulated in the high pressure compressor loop, that is upper loop, that is what? M2 dot. So this we will use for the next analysis purpose. Now the points are, all the points we will see across the compressor 1, point is 1, 2, then 2 to, there is a entry. This is a vapor line coming out, point number 3. So 3 is a entry to the compressor 2. 4 is the output of the compressor 2. 4 to 5 is a condensation. 5 to 6 expansion in high pressure loop. 7 is a exit of the flash chamber, liquid line. Then 7 to 8 is a expansion process, and 8 to 1 is a evaporation process. So now if you see here, it's a pH diagram, then you will see here pH diagram. In the pH diagram, this is a entry of the compressor 1 which is coming from the evaporation process. So 1 to 2, this is a compression 1 LP, low pressure. 3 to 4 is a compression 2, 4 to 5 condensation. Then expansions in a upper loop 5 to 6, and this is the expansion in lower loop, that is a low pressure compression. 5 to 6 for the high pressure and 6 to 7 for the low pressure. So now here we can get the enthalpies when we will solve the numerical. Normally what we do, we project the vertical lines from the points which are on the chart. So here 1, 2, 3, 4, then 5, 6 both are same because isenthalpic process. 6, 7 both are same, because here also isenthalpic process. So in this way we find all the enthalpies from H1 to H8. These enthalpies we use for solving the numerical. Now here on the left side here, while drawing the while plotting this cycle, we require here temperature of the evaporator that is given in the numerical, that is a negative temperature. This point is a dry saturated point, and this point number 5, that is a ambient temperature to which condenser reject the heat. So this data from the numerical we use, and we plot the, first of all locate the point number 1 and point number 5, and then in the numerical also it is mentioned that is at a flash tank pressure, that is intermediate pressure. So with the help of that pressure value on this pH on the pressure scale, here we can take reference and we draw this line. Then from this point when we draw remaining lines, that is vertical line, horizontal line, here vertical line, horizontal line, from 1 isentropic line, from 3 isentropic line. When these lines we draw isentropic line, these two lines will meet to corresponding pressure lines, and then intersection points, that is what exit of compressor, low pressure compressor here, and exit of high pressure compressor here. In this way we can obtain these points on the chart. Now let us do the analysis of the system, complete two-stage compression system. In the analysis, first what we do, first of all we calculate the mass flow rate. So for the mass flow rate formula is what? Cooling load capacity formula. Cooling load capacity will be given in the numerical, Q dot L. Q dot L will be equal to what? Process which is happening here, mass flow rate, that is M1 dot. M1 dot multiplied by this refrigerant effect, means H1 minus H8. H1 minus H8 multiplied by M1 dot will be what? Cooling effect. So here we have written this formula, Q dot L is equal to M1 dot into H1 minus H8. This in kilowatt. Now as the Q dot L is given to us in the numerical, we arrange this formula for the mass flow rate, that is equal to Q dot L divided by enthalpy difference. So by solving this formula in the numerical, by putting the data, we can obtain the mass flow rate of the compressor 1. To find the mass flow rate of compressor 2, we have to use energy balance equation of a flat chamber. So here we use the concept what already we discussed in the previous two systems, that is amount of heat entering to the system is equal to amount of heat content leaving the system. So let us go for to the construction diagram before coming to this equation that we will see in a diagram, that is construction. So in the schematic diagram here you can see this is a flat chamber. At the flat chamber, if you find the lines which are entering and leaving, you will find here 4 lines. 2 lines entering and 2 lines leaving the flat chamber or flash tank. So here entering lines you see from the compressor 1, this is the entry line. So here entering line product of what we do to find the heat content, corresponding mass flow rate M1 dot, that is of compressor 1, and the compressor exit enthalpy H2. So M1 dot H2, this will be heat content entering to the flat chamber, M1 dot H2. Another heat content which is entering to the flat chamber, that is what this line which is coming from the condenser and passing through this expansion wall to the flash tank. So here mass flow rate which is coming from the compressor 2, that is M2 dot, and after the expansion wall here the location point is 6. So M2 dot H6. So here product of M2 dot H6 will be what? Amount of heat entering to the flash tank. So we have seen now 2 heat contents entering to the flash tank. One is M1 dot H2, another is M2 dot H6. This will be on the left side of the equation. Right side of the equation will be what? Heat content leaving the chamber. Now here are 2 lines leaving. First line, if you see here, then this is a line which is leaving. This is a point number 3. So enthalpy will be S3. And this is a mass flow rate of the second compressor. So M2 dot H3, this is a heat content, will come on the right side of the equation, heat content. Another living line is this liquid line, which is going to the evaporator through this expansion wall. So here this will be point number 7. And mass flow rate will be what? Here in this envelope, low pressure compressor. So mass flow rate is what? M1 dot. So product of M1 dot S7. So addition of this M2 dot H3 and M1 dot S7. These two will be on the right side of the equation. So here you can see now energy balance equation, what we discussed. Total energy in is equal to total energy out. These are the two lines which are entering to the flash chamber. This is of compressor 1 coming out and going to the flash tank. And this is from the condenser coming and going to the flash tank. So these two lines, summation product of mass flow rate and respective enthalpy. And these two lines which are coming out of the flash chamber. This is a line which is going to the compressor 2. And this is a line which is going to the evaporator, liquid line, which is coming from the bottom of the flash tank. So in this way, here, this energy balance equation we use to find the mass flow rate M2 dot. So here, in the analysis, we use the equation that is a capacity equation, refrigerant effect equation to find the mass flow rate 1 of low pressure compressor. And this heat balance equation we use to find the mass flow rate of high pressure compressor, that is M2 dot. Now these two mass flow rates, M1 dot and M2 dot, we can use further for the calculation of compressor consumption. In a work consumption, here will be two formulas. Low pressure compressor, that is a C1 compressor. Consumption is what? W1 dot is equal to mass flow rate M1 dot multiplied by H2 minus H1 is the enthalpy difference across the first compressor. W2 dot is a consumption of second compressor, that is high pressure compressor, that is equal to M2 dot mass flow rate, and corresponding enthalpy difference, that is across point number 3 and 4 is H4 minus H3. Then sum of these two consumptions, compressor 1 and 2, will be what? Net consumption, that is what we call as power required to run the system. So power required to run the system will be what? W dot is equal to W1 dot plus W2 dot. Now all these consumptions are in kilowatt. Finally, coefficient of the performance is what? Capacity in a kilowatt, cooling capacity Q dot L divided by net consumption, power consumption, W dot. So this is what? Coefficient of performance. So in this way we have seen complete descriptive explanation of the two-stage multi-stage, two-stage multi-pressure compression system, its schematic diagram, then pH diagram, and after the pH diagram, formulas for the compressor mass flow rate, that is the low pressure compressor, mass flow rate circulating through low pressure compressor 1, mass flow rate M2 dot which is circulating in the high pressure compressor. Then after that we have seen the consumptions, compressor 1, consumption compressor 2, then sum of these two, that is a net power, and then COP, that is a output divided by input. In this also we have seen to find the mass flow rate 2, energy balance heat balance equation at the flash chamber. So in this way now we can use this theoretical idea to solve the numerical of complete multi-stage compression system in the next video session.